gonna explore the limit a little bit more. We're gonna look at it in some simpler contexts and things like that. So let's go to section 2.2. So this top of the page is just a quick review of the phrases we already said. From the last section, we saw that a limit occurs when finding the instantaneous rate of change of a function. And recall that this is the same as finding the slope of the tangent line. To find the tangent, you just essentially consider the limit of the secant, and then eventually get so close that we end up with the tangent. So we'll talk about the tangents and the secants a little bit more in chapter 3, as that's very much related to something known as the derivative. We're actually going to think more about the process of limits in the rest of chapter 2. So limits are used when we're interested in a function's behavior near a particular point C, but not actually at C. Up to this point, our main focus has been really on computing things like f of c. What is f of c? Well, you look at the graph, you follow like, okay, given x, there's my y, or you plug it into an equation. So at is more of a focus at f of c, where really, when we're talking about near, we're going to talk about what happens when x approaches c. So there's very different notations associated with it. But it's going to take some time because, again, now things are changing. Before things were static, we were able to say that's where it's at. But now we have to kind of think about what is it doing as it moves. So there's this more of a dynamic thought process compared to the static one. But we have an example to kind of start us this idea off of limits and what is happening near. How does the function f of x equal to x squared minus 1 over x minus 1 behave near x equal to negative 1? Well, maybe to start us out, let's kind of think about what is the domain of this function really quick. If you were looking at this function that I'm giving, this rational function, what is excluded from the domain? 1. So notice the domain here is essentially, I'm going to just write it kind of like this, where x cannot equal 1. So another way to think about this is to say that f of 1 is undefined. We can't even talk about like what is happening at 1 because it's not defined there. So that's why we're now going to transition to this idea of near. So again, maybe just to fill out this f of 0, the issue is that we get 0 over 0, and that is undefined. Let's consider some values near 1 now. So let's consider what happens that should have been f of 1. So f of 1 is equal to 0 over 0, just plugging it in, you have that issue. Let's pick values near it now. So let me change to red. So we have f of 0.9. If you look at f of 0.9, we have this already computed for us down below. This is going to be 1.9. Or if you consider just above it, like f of 1.1, and you actually plugged that in, and you did like 1.1 squared minus 1 over 1.1 minus 1, you'll end up with 2.1. So just kind of showing the computation there. That's already taken care of us down below. So, and then let's consider let's get a little closer. You know, it's like you're like, first, it's like when you're a kid, you're like, can I touch the oven? I'm going to just get a little closer. Or in my case, the cookie jar. I'm going to get a little closer and closer. So let's get a little bit closer. Let's say f of 0.99. We plug that in. We see the computation down here, and we end up with 1.99. And then if you plug in, let's say 1.01, get a little bit closer to 1, you'll see that down here below we get 2.01. And if we were to continue in this matter, if we were just, okay, we have 1.9, then we have 1.99. If we were to continue in this matter, what value are we going to keep getting closer and closer to? You will see it down here below. We seem to be getting closer and closer to 2. And if you look at this 2.1 and then 2.01, in the same way, we're getting closer and closer to 2. So what we really could say, and we can boil down this process and we'll look at techniques to make this easier, what we can really say is the limit as x approaches 1, as x gets closer and closer to 1, of this function, x squared minus 1 over x minus 1, it is equal to 2. This 2 right here is the limit L. It's the y value that we're approaching. So I'll say this multiple times because it does help for me to repeat myself. Though this is a y value. So if we look at this, we did it computationally that time, but let me kind of point this out here, down below. Notice that there is a hole in the graph right here at x equal to 1. Hence we said it's not part of the domain. Does anyone remember in a rational function what happened when there's a hole in the graph? What happened when you were maybe playing with the function? Does anyone remember? There was a cancellation. So if you think about this function right here, this is just a difference of squares, x plus 1 over x plus 1 times x minus 1 over x minus 1. Notice again, there's a cancellation of the x minus 1s, which caused that hole. So remember that whenever you're dealing with rational functions and you cancel because of some factorization, that does not put that number in the domain. It just says there's a hole in the graph there. So while we could not talk about what is actually happening at x equal to 1, we can check and see what's happening near x equal to 1. So notice again, there's now some dynamic to it. I'm going to approach this 1 from the left. So notice when I'm approaching it from the left with the x's, I'm also going to have some corresponding y approaching it. And then the same way, I'm approaching it from the right-hand side. I'm also approaching this from the right-hand side. And if you look at these matching right here, notice that these are now pointing to the same spot. What y value are they pointing to? 2. That's the graphical representation of the limit. So the actual computation we did here kind of shows you the computation of a limit by plugging in values. But if you notice that as you approach x from the left or the right-hand side, and it's pointing at the same y value, that's when you actually go ahead and see the graphical representation of the limit. So that's the basic idea. We're going to explore the computations, the graphical side more in today's lesson. But now we just kind of flesh out those ideas. So this idea is sometimes referred to as the informal definition of a limit. We'll talk about the formal definition in the section 2.3. So this is the informal. So if f of x is arbitrarily close to a number L, and again, let me say L, what did I say it was? Was the limit an x or a y value? What did you guys recall? Good, grab onto that. The limit is some sort of y value. The limit L for all sufficiently x close to c, we say that f approaches the limit L as x approaches c. We write that as follows. The limit as x approaches c of f of x is equal to L. The limit as x approaches c of f of x equals L. So there you now have a kind of the English representation of the symbols I wrote above. So, and we already did rewrite one using this last page. On the last page, we did that as the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to 2. We already did that on the last page, but there just to have it for the sake of completion. So down here, we have three different graphs. All of these, there are three different functions. We have f of x, g of x, and h of x. Notice them, they're each a little bit different in how they're behaving at 1. So notice in this first case, f of 1 is undefined. So I should technically just say f of 1 is undefined. Or I'm going to just put und for short. G of 1, so this middle graph, g of 1 is defined piecewise to be equal to 1. So right here, g of 1 is equal to 1 because I go to this x value, I find the graph, and the associated y value is there. And you can see that's also from this piece right here. And in this last case, h of 1 is just going to be, well, you can see it up here, it's going to be 2. So notice these three different functions behave very differently at x equal to 1, but each of these functions have a limit of, well, the y value 2 as x approaches 1. And maybe I should have called this out explicitly above. This little arrow is read as approaches. Just wanted to make that point. Get it? Because it's pointing? Okay. I thought about that one for class. That's what happens if you don't distract me. So note that the limit of the function, it does not depend on how the function is defined at the point is being approached. All three of those had very different behaviors at 1, but in all of these scenarios, if you were approaching 1 from both sides and kind of translated those arrows to the graph, you would be pointing, in both of these cases, you would be pointing at 2. Does everyone see kind of how I'm looking at this? I'm taking the x values, I'm approaching it from both sides, and I'm translating those arrows to the actual graph. And if I'm pointing at the same y value, that's telling me the limit. Okay. For the limit to exist at a point C, it is only necessary that it approaches the same value from both sides. In section 2.4, we're going to drop that two-sided requirement. In 2.4, we're going to talk about one-sided limits. So we'll only consider what is happening from the left or from the right. Right now, we're going to go ahead and consider both to make sure the limit exists. So let's go ahead and make sure we understand this graphically using this example down here below. Okay, I'm going to go ahead and do maybe the first example, and then I'll give you some down here at the bottom just to break up the day while I take attendance and the like. Any questions so far? Okay, if there's ever questions, always feel free to ask. So in this case, we're given this piecewise function, g of x. We're not going to worry about what is the actual pieces. We can go ahead and define it if we wanted to. We want to find the limit as x approaches 1 of the g of x. So what I'm going to do, I'm going to look and see 1 right here. So I'm going to approach that x. Let me make my pen a little bit bigger. I'm approaching that from, is that green easy enough to see? Okay. So I'm going to approach 1 from the left and the right. And then I'm going to go ahead and translate those arrows to the graph. Am I pointing at the same y value? This one up here is pointing at y equal to 1. This one right here is pointing at y equal to 0. Notice that they're pointing at different y values, so we'll simply say the limit does not exist. So in this case, the limit as x approaches 1 of g of x does not exist. When I'm lazy, I am going to just say D and E or Denis. There's no Denise in here for me to confuse, so I'll just say Denis, or it does not exist. So again, maybe just to put in words, what I saw is notice that the y values approached differ. In that case. Let's do a couple more together. In the case of B, we're looking at 2. So notice I'm approaching 2 from the left and approaching it from the right. And by the way, I always want to kind of look at it really close to 2. I want to be near it. I don't want to be looking at like I'm approaching 2 from over here because the graph's doing all sorts of funny things over there. I'm just going really near, just near enough where the behavior is consistent. So we can see that if I translate these arrows up, I get this and this. These are pointing to the same y value. What y value are they pointing to? 1. So the limit as x approaches 2 of g of x is equal to 1. Let's go ahead and do this. Let's do that orange. So 3. So I'm approaching it from the left. I'm approaching it from the right. And I'm looking at the arrows on the graph. Are both of the y value arrows pointing to the same y value? What y value am I pointing to? 0. Careful, don't think about the x. Remember, the limit is going to be some y value. So in this case, indeed is going to be 0. But what is g of 3? G of 3 is 1. G of 3 is up here. Notice that the value at and near do not match. When they do not match, what do you see in the graph? We see a hole. But notice when they do match, it's continuous. Let me say that again. Notice, again, let me write this in red. Notice that in 2, g of 2 is 1. So notice that that these match. When those match, it's continuous. That's section 2.5. So that statement right there is going to be unpacked in section 2.5. And then one more example. We were using nice integer points, but let's do something that's kind of in between. So here's 2.5. So there's going to be 2.5 right here. I approach it from the left and from the right. I'm going from right here to right here. What is the limit? Because it's pointing at the same one. I don't know. What do you guys say that's about out? I just want to say 0.5. So right there is 0.5. So the limit as x approaches 2.5 of g of x is equal to, running out of colors here, is equal to 0.5. And I kind of ran out of room. It's there, and there. That doesn't work, but 0.5. Any questions where we got any of those values? Okay. So while I take attendance, slide down to this example down here, and instead of the computation side, it's more asking it in true or false. So go ahead and let me give you a minute or so to go ahead and do number 3 and answer for each of those statements true or false. We'll go over, I'll put up the answers here in a sec, and then I'll clarify any that need clarified. Right? Yeah. All right. All right. Haley, Luke, and Raoul, Chapel, Destiny, Haley, Caleb. Sarah, Cadence, Weston, Grace, Josie, Alfred, Savannah, Griffin, Say, Emma, Sarai, Christina, Marina, David, Roxana, Hoyt, and James. So up on the screen, I have the answers. Let me give another minute just to kind of process your work. And then if there's any that anyone would like explained, feel free to ask. Yeah. They exist at every point. Sure, so like D?
Yeah.
So D is saying the limit as x approaches c of f of x exists at every point c in this interval. So what this is saying from this -1 to 1, let me highlight the part of the graph we're looking at. So we're looking at this little piece right here. So basically you're looking at everything in here, and do you ever see a scenario where the limit doesn't exist? So you basically are going to be considering it as it approaches here. And this is a good point you brought up. The fact that the graph doesn't exist over here means we don't have to worry about the limit. So you can see that it does approach right here. It approaches, oh wait, actually it doesn't even, never mind, this is an open dot. So it does not include, so ignoring -1 to 1, because that would get into like one-sided limits, which we're not ready for. But if you look at everything inside of here and you were just to say, okay, the limit as x approaches 0 of f of x, that is equal to 0. If you were to do the limit as x approaches, let's say like -0.5, well, that would be about right there. So that would be -0.5. So in every single x value or c that you choose in there, it exists, then that statement is true. The issue would be if there was something like a gap like this right here. So the issue would be like if you tried to do from like 0 to 2, it does not exist there. So that would be something to watch out for to make the statement false. Great question. Does that help? Perfect. Any other questions about anything on 3? All right, then let's go ahead and move on. So this is the graphical approach to working with these problems. To work with the actual equations, we're going to find that we can boil more or less everything down to 2 simple functions. We have this first function right here, f of x equal to x. Anyone remember what this function is called? Anyone have any ideas? It's your identity, yeah. This is your identity function. The way the identity function works is whatever you plug in, you get out. So f of 3 is equal to 3, just to make this more a little concrete. Let's just consider x naught is equal to 3. So let's just kind of let x naught equal to 3. By the way this is read, you'll sometimes see this notation. Instead of using c, they'll use x with a little subscript. This is either read as x sub 0 or x naught. Does not have a k on it? The silent case. If you don't know what you're doing, you'll have trouble with them. Okay. Anyway, so the thing to note about constant functions is let's just consider the limit as x approaches 3 of the constant function 3. I wrote that. Of the identity function. Constant functions down below. So let's consider the limit as x approaches 3 of the identity function x. Well, what would it be? If you approach 3 from the left and from the right, you notice what y value are you pointing to? You're going to also be pointing to 3. So again, kind of notice the matching up here of that. And notice that the identity function will always have this diagonal line. This is a graph. If you chose 1, you would be at 1. If you chose pi, you'd be hungry, but you would still be at pi. So again, if you look at this, let's do those 2 other examples. The limit as x approaches 1 of x is 1 because it's going to be right along the diagonal. The limit as x approaches pi of x is going to be equal to pi. Anyone want to take a stab at what the limit as x approaches 391.5 of x would be? the value of x we're approaching, exactly 391.5. So again, that's a nice, easy function to work with because the diagonal is going to be where x and y are equal. So you can go ahead and just notice that the limit will be the same as the value of x we're approaching. So that is the identity function. Anyone have any, maybe let me also write this in general. In general, what we have right here is that the limit as x approaches some constant of x is the constant that we are approaching. So that's the kind of the general idea. You may notice, can I just plug in the value we're approaching? It's something to try. Let's go ahead and consider this other function down here below. This other function down here below is the constant function. So notice that k is a constant. To make this more concrete, let's just let k equal to 3. So let's consider f of x equal to 3. So just to kind of get this a good grasp on this function, f of 3 would be equal to 3. F of pi would be equal to 3. F of 42 would be equal to 3. That's the constant function. Y values, what do you notice is the y value? What is it always going to be? 3. So if you think about this, whatever x value you're approaching, when you translate that to the graph and see the y value, it will always be whatever the constant is. So this would say so all of these, the limit as x approaches any, let's just do 0 of 3 is 3. The limit as x approaches pi of 3 is 3. So let's see if we kind of have spotted a pattern right here. Let's be careful. What is the limit as x approaches 10 of 11? How many think it's 10? How many think it's 11? Many of you are right. It is the function, because remember, this function right here is associated with the y values, and the limit is the y values. This x is the value we're approaching. So what about the limit as x approaches pi of the square root of 2? Square root of 2 is a constant. What is the limit right there? It's the square root of 2. In general, we have this kind of pattern right here. The limit as x approaches anything of the, you might want to write it like this? Yeah, this will work. Any value of x is going to be equal to the constant k. So be careful, when it's the constant function, it is going to be the function giving you the y value. So again, just make sure, let's do this in orange, that k is transferred over. So those are the two basic functions that we kind of can see that the principle from graphically. And on the next page, bless you, we talk about where the limit doesn't exist. We'll just look at this more in 2.5. That's kind of a detour that I don't really want to take right now. So limitless, I guess he's reached his limit. So let's just move on to the limit laws. So I'll say more about the limitless scenarios in 2.5. So the limit laws will allow us to go ahead and take those two properties that we talked about with the identity and the constant function and work with pretty much every function we know about. We still don't have a rule here for compositions. We'll talk more about that one in 2.5 as well once we have continuity in play. So the limit laws basically say this. If you have two different functions with their own limits, when you add the functions together, you add their limits. When you have two different functions with their own limits, as x, and I should have specified, and they're approaching the same x value, you can subtract limits. You can multiply limits by constants. You can multiply limits. You can divide limits. You can exponentiate limits. You could take the square root of limits. So these laws, along with our discussion about the identity function, simply allow us to plug in c, the value c we are approaching, to find the limit. So let me kind of highlight the important part there. It's already italicized. The first thing we're going to try, because of these limit laws, is we're going to just try to plug in the value we're approaching to evaluate the limit. Because if it is, and this kind of goes back, no need to turn there, but just to kind of emphasize and connect it to what we said earlier, because if it is the same at and near, you know what, we might as well just talk about it at. Because if it's the same at and near, we might as well talk about it at. So let's figure out how to compute this limit. Find the limit. Let's do 5 first. You know what? Let's do 4. But let's change it. C kind of looks like a 6. Let's just make this a little more concrete and just make that a 6. Tuscana is so far away when it's raining. Dang. Okay. All right. So focus. Lunch, hungry, food, math. Okay. So let's change this to 6. Just to make sure that it's a little more concrete. So what you're going to try to do to find the limit, just try to plug in the value you're approaching. So we'll have 6 cubed plus 4 times 6 squared. Should have picked a smaller number. Oh well. Minus 3. Notice that when I plug it in, that limit is gone. 6 cubed. Thank you. Plus 4 times 36 minus 3. So 216 plus 144 minus 3. What is it? Thank you. 357. I'd like to pre-do my arithmetic because I get nervous doing math in front of all of you. So what we have right here is that the limit as x approaches 6 of this cubic function is equal to 357. So to find the limit, first thing you'll try is just plugging in the value you're approaching. So go ahead and take a look at 5. Let me see if that idea stuck and see that if you can find the limit for number 5. Plug in the value you're approaching. Yes, in this case, 1. Because when at and near are the same, we could just go ahead and consider plugging it in. So we have 1 to the 4th plus 1 squared plus 1 minus 1 over 1 squared plus 5, which is 1 plus 1 minus 1, which is 1 plus 5. Did you end up with 1/6? Very good. Let's look at a few more examples. The limit laws allow you to consider the limit or functions inside the square root. So don't be thrown off by the square root. Still, first thing you should always try when evaluating limits is plug it in. So you get the square root of 4 times minus 2 squared minus 3, which is going to be the square root of 16 minus 3, which is the square root of 13. The limit as x approaches minus 2 of the square root of 4x squared minus 3 is the square root of 13. Okay. What about 7? Go ahead and try 7. I'll just work this one silently. Oh, and the 8 on the outside. That 8 is so sneaky. That's not a 6. That is 8. Yeah. Thanks, James. Good catch. I just didn't want to write it because it was going to make me hungry. No, that was a terrible excuse. Don't use that one on the test. You're not allowed to use that on the test, right? I didn't want to write the 8. I was hungry. It was lunchtime. So what we should end up here with is 8 times 1 times minus 1 or minus 8. This example illustrated, again, that we don't necessarily have to always work with x. T is another common one we'll work with. In the case of 8 and 9, we do have some trigonometric functions. 8, I'll just remind you, again, don't get thrown off by theta. You can actually rewrite this problem if you prefer x better, that this is the limit as x approaches pi over 2 of sine of squared of x. Remember, another way to write the square, I'm going to just read, is to square the whole thing. So just keep in mind that what we're really doing here is going to be sine of pi over 2. All of that squared. Notice again, when I plug it in, the limit is gone. So sine of pi over 2, what is that? That's 1. 1 squared is 1. Okay. What about the secant one here? Remember that in secant, you are just considering 1 over cosine of x. So number 9 shows that you're still allowed to go ahead and do algebraic manipulations before you consider the limit. So let me say that again. We'll explore more of this next class. You're still allowed to do algebraic manipulations before you before you take the limit. So notice the limit's still there. On the next step, when I plug it in, the limit's gone. So if you see the limit still there on a step, what I probably just did was some sort of algebraic manipulation, which we'll find is necessary in a lot of cases. These are kind of your basic examples. But once the limit's gone, it's because I plugged this in. So this is 1 over negative 1, which is just negative 1 is our limit. Any questions on 8 or 9? So one thing that also keeps in mind is number 10. There's a lot of weird symbols here. The limit as x approaches the square root of 10 of 2 pi. But my suggestion is, again, always make sure you think about what type of function. What type of function is 2 to the pi? Constant to a constant is a constant. Think about this as 2 to the third. 2 to the third is 8. So this is approximately 8. With that in mind, what is the limit as x approaches x approaches the square root of 10 of 2 to the pi? It's that constant 2 to the pi. So just be careful with that. And last one, just to make sure what about if we were to consider the limit as x approaches the square root of 10 of 2 times x? Volunteer? Who wants to end us out today? Who wants to be the person to release the class? 2 rad 10. Very good, Griffin. And with that, he has freed you all. Go have a wonderful day. But if you do have questions, feel free to stick around. We'll pick up where we left off tomorrow. So let's go ahead and pick up where we left off last time. And that was where we were finding the limit. So last time, at the end of class, we kind of learned the general procedure when approaching or when finding the limits of an equation or of a function. So the first thing we should always do is try to plug it in. So hopefully that smells good because it sounds like a Glade commercial. We're just trying to plug it in. So that's always the first thing you should try. So if I look at this right here, I see that the value of x we're approaching is 1. So I'm going to just go ahead and try to plug that in. I get 1 squared plus 1 minus 2 divided by x, well, let's substitute 1 squared minus 1. What we get here, though, is, let's see, in the numerator, we get 1 plus 1 minus 2 divided by 1 minus 1. So ultimately, when the simplification carries out, we get 0 divided by 0. This is an issue for a couple reasons. We can divide by 0. It's not defined. And this right here is actually referred to as something known as an indeterminate form. So indeterminate determinate form. 0 over 0 really does not have any sort of representation in terms of the real values in most cases, but we can do various things when we run into this. So 0 over 0, let me actually not circle that because it's not that is not the limit. 0 over 0 is not a number. So it's something known as an indeterminate form. So unfortunately, we just kind of have to do this, cross out this part. That did not get us the limit. But what it did tell us is that there's a common factor. So if you're so step 1, with one's like maybe just up here, find the limit, find limit. The step 1 you'll always want to try to do is just plug in the value we are approaching. And let me be more specific, the x value we are approaching. But whenever you get 0 over 0, it's because there was a common factor. So what we can go ahead and do, step 2, is try factoring and canceling. Does canceling have 1 or 2 L's? Sounds right. I guess the other L.
It's 2 and 8.
I guess that second L got canceled over here. Anyway, so let's go ahead and this next step, I am not going to go ahead and get rid of the limit because I'm not plugging anything in here. What I'm simply doing is factoring this as x, plus 2 times x minus 1. And then I can also factor out a common x in the denominator, leaves with x minus 1. So again, I just factored the numerator and the denominator, but we see there is this common x minus 1. Whenever you try to find the limit with 0 and you get 0 over 0, there's going to be a common factor. So what we now have is that the original limit is equal to the limit as x approaches 1 of x plus 2 over x. And then let's go ahead and try and plug in 1. We get 1 plus 2 over 1, which is going to be 3 over 1 or just 3. This right here is the limit that we were looking for. Let me also just check if you all remember the limit 3. Is that an x or a y value? Very good. That is a y value. So let me also just check for understanding before I show the graphs completely. Whenever there was a cancellation, what did that mean about the graph of the rational function? That there was a hole. So again, the fact that there was this cancellation here means that there was a hole. And you can see that hole right here in the original graph. When we cancel this new function right here that we're looking at, notice this new function is different because it has the hole, but the limit is the same. Because the limit, we just cared at what we were approaching, not what was actually happening there. So again, remember the idea we took last time, that when we're approaching 1 from the left and the right, we take the x values, we translate those arrows up to the graph, and we look at what we're pointing at. We're pointing at y equal to 3. That right there is our limit. And it does not matter if there's a hole. If you are still pointing at that same y value despite there being a hole, so again, the cancellation is okay, it does not change the limit. So the first step, again, always just try to plug it in. If you get 0 over 0, try factoring and canceling. We're going to run into various other scenarios. If you can't plug it in, you're probably just going to have to do some sort of algebraic manipulation, whether it's using a trig identity, your logarithmic properties, some basic just combining like terms. So this idea of a hole being in the graph shows up briefly in another idea. Let me see if I talk about it here. Oh, I don't talk about it yet. I talk about that in section 2.5. This idea of a hole being filled is we'll talk about again in 2.5. It's called a continuous extension. More on that later. So we have 2 more examples down here. So let's try and do number 12, the limit as x approaches 5. What are we supposed to try first? Always just try plugging it in. So when I try plugging that in, I'm going to just do it horizontally first. I get 5 minus 5 divided by 5 squared minus 25, which of course is 0 over 0. Because we got 0 over 0, there's a common factor that could cancel out. So I'm going to go ahead and just kind of cross this out. That did not work. Oh well. But I'm going to go ahead and do some factoring. Remember that this factoring that we'll do in the denominator is known as a difference of squares. Both x squared and 25 are perfect squares, and they're having a fight. They're having a difference. Whenever they're having a fight, we break them up, because that's what you do when siblings are having fights. So we break that up as x plus 5 times x minus 5, and we have a cancellation of the x minus 5s. So we're now considering a similar function, the limit as x approaches 5 of this time 1 over x plus 5. And we can just go ahead and plug in the value we're approaching here to get 1/10. So that's how the limit works from a computational perspective involving rational functions. Any questions on those two examples? All right, well, I'll take a quick look at attendance. Go ahead and try 13. A little bit going on, but see what you can remember. It's just an example using a different variable as well. Let me take attendance. Haley, Joe, Luke, Emily, Raul, Chapel, Destiny, Haley, Caleb, Sarah, Cadence, Weston, Josie, her, Grace, Alfred, Savannah, Say, Emma, Griffin, no Griffin tag, Emma, Sarai, Marina, David, no David today, Roxana, Orlin, and James. So the limit, when it's all said and done and simplified, is a negative 1/2. If you're good on that one, just give me a quick little thumbs up. Does anyone have any questions or anything I could clarify? Great. Yeah, James. Why did I get rid of the 5 and these right here? So again, as we get more comfortable with things, I'm just kind of like simplifying things in my head. Like when I plug in 0, I know this whole term is going to go to 0 anyway. 0 is a nice number. If anyone asks me what my favorite number is, it's usually 0 or 1, just because they're easy. I know it's kind of lame, but they're nice to work with. But if I really had to pick my favorite number, 42 is fun for anyone who's read. Has anyone read Hitchhiker's Guide to the Galaxy by Douglas Adams? Yeah, it's the answer to the ultimate question of life, the universe, and everything. So it just makes that number sound really epic. But great book, great movie if you ever get a chance to watch it. It's really kind of a fun little watch. So Hitchhiker's Guide to the Galaxy. All right, so that was 12 and 13. So there's other things that we're going to run into. So we're going to just talk about some other situations you may run into with evaluating limits. So we're going to look at 14, 15, and 16. We'll maybe pick one or two of these to do. This is kind of very similar to the one I said we'd skip back in section 2.1 involving the square root. So we'll come talk about this chart here in a sec. We'll come back to that. So if we go ahead and just, of course, the first thing we should always try is what? Plug it in. So I'm going to try to plug in 0, and I get 0 squared plus 100 minus 10 over 0 squared. And this, of course, is going to be 0 over 0. And you kind of saw the pattern. We're gonna run into that. So I'm just going to kind of cross that out. That did not give us the answer. So there's an interesting idea. If you were plugging this, let's suppose you were trying to find the limit computationally. And remember, the idea is the limit is you get closer and closer. So again, notice here we're 1 away. Notice we're 0.5 away. We're getting closer and closer at each one of these steps. So if you notice when we go ahead and consider these, we're getting close. It looks like we're approaching 0.5, don't you agree? But look at what happens when you get really close. When you're only 1/10,000ths away, all of a sudden it goes to 0. So why does that happen? This is actually a limitation of the technology that we use. So it does not approach 0. We're going to verify algebraically that approaches 0.05. But the reason that this is happening is because something known as basically floating point error. Floating point. This is a limitation of the technology we use because numbers could go on infinitely, but the tools we have are still finite devices. I think depending on the data type you're using, but a computer only could store typically 32 or 64 bits to represent a number. So this error has actually caused an explosion of a rocket. So because the programmers weren't careful with this error. I'll see if I could find that video and post it. So we're not going to be reworking about it, but it's just something as simple as a floating point has caused disasters. I can't remember the full story, but I'm going to go ahead and find it later. So it's interesting that though the idea is that here we are talking about things that are truly infinite, but we're finite beings. We have finite tools. So I don't know. I always like to think maybe calculus helps us understand God a little bit more. Infinite being. How can we think about it in terms of our infinite tools and our finite tools and our finite minds? Shows up a lot more in Calculus 2 where we talk about convergence, but I don't know, just throwing it out there for now. So on 14, okay, we got 0 over 0. If you look at this, does anyone see a way we can factor and cancel? We haven't really encountered anything with this. So if you remember back to when we were working with complex numbers, you would always go ahead and multiply by the complex conjugate to cancel things out. So here's kind of the trick. It's kind of a unique approach that works only with radicals. What I'm going to do is I'm going to just rewrite my original problem right here. So we have the limit as x approaches 0 of x squared over 100 in the square root minus 10 all times x squared. What I'm going to do is I'm going to multiply both top and bottom by the conjugate. That is to say, the square root will stay the same, and I'm going to change the term in the middle, is sine, to its opposite sign. Of course, if I multiply that in the denominator, in the numerator, I have to also multiply that by the denominator. Because of the change of sign, we're going to have some cancellation when we FOIL. And we'll find that that's going to play out really nicely to cancel that x squared that's causing the issue in the denominator. So again, this is equivalent to our original problem. So we're going to bring down the limit as x approaches 0. I'm not plugging in 0 yet. I'm just doing some algebraic techniques. When I FOIL, a square root times a square root will just give me the radicand inside. So there's my first. Is everyone, I'm not going to write this, but if you look at the outside and the inside, does everyone agree that those are going to be the same numbers, just different signs? So I'm going to cancel them right here. One will be positive, one will be negative. So we'll end up with just a minus, I'll color code it in green actually. This times this is going to give us a negative 100. In the denominator, I'm not going to distribute. I'm going to just leave this as x squared times the square root of x squared plus 100 plus 10. To see why I didn't distribute, notice again that the hundreds will cancel. And then once the hundreds cancel, the x squareds will cancel. Because you'll have an x squared in the numerator and the denominator. And again, once the x squareds once the hundreds are canceled, there's no parentheses to prevent the cancellation. So what we have then is still haven't taken the limit yet. We're still just consider the limit as x approaches 0 of 1 over the square root of x squared plus 100 plus 10, which is going to give you, now when you take the limit, 1 over, let's see, square root of 0 plus 100 plus 10, which is 1 over 10 plus 10, which is 1 over 20, which is 0.05, which that table was showing above. So that's kind of another kind of niche technique that you can use whenever you can't factor to cancel. Yes?
Why didn't you simplify the numbers in the radical?
So the question right here, and there is this temptation just to be like, oh, square root of 10, or squared, the square root of x squared and the square root of 100. You cannot do that because remember that radicals are like exponents and you cannot distribute those over addition. You could only distribute that over products. So if this was x squared times 100, then you can write this as the square root of x squared times the square root of 100, but addition does not have that property. So I know you see perfect squares and you're like, oh, I just feel like I should be able to do something there. Unfortunately, we can't because of the addition. But if it was multiplication. Is that what you were asking? Yeah. So it would have been nice, but can't do that there. Any other questions on this one? All right, so this is a little bit of a weird technique. So go ahead and try 16. While you do 16, I want to see if I can find that video really quick. I just think it's pretty fascinating and kind of tragic at the same time. Yeah, here's the a little bit of information about it. It was actually an explosion of the Ariane 5 rocket launched by the European Space Agency. And it kind of happens like right here, where it was talking about they were trying to represent, they thought they had 64 bits to represent a decimal or a floating point number, but it got messed up when it was trying to convert to 16, so it messed up the velocity and ended up costing about $500 million. So I'm guessing someone lost their job over that, but it's still pretty tragic. So anyway, if you're playing around on your calculators for plugging in really small values, realize that that problem does exist in the technology we use today. Okay, let me go ahead and show the work for this. Does anyone want me to talk through it, or do you want me to just write it really quick? Sure, I'll go and talk through it. Sure. All right, so the first thing I'm always going to try is, well, plug it in. So 1 minus 1 over the square root of 1 plus 3 minus 2 is going to be 0 over 0. Unfortunately, it just wasn't that simple on this problem. So I'm going to slide this out of the way. And what I'm going to do is I'm going to take whatever the square root is. I know up here it was in the numerator. You would just always look for whatever the square root was. So the fact here it was in the denominator. And this will be the square root of x plus 3 plus 2, because when we FOIL, we want it to cancel out. And then we'll still go ahead and whenever we multiply by that x plus 3 in the square root plus 2 in the denominator, let's also do it in the numerator because we can only multiply by a factor of 1. The number over itself, of course, is 1. So when we do this, the limit will come down. I'm not doing anything with the limit yet. I'm just doing some algebra. My suggestion, again, is always just to go ahead and leave the part not involving the conjugate alone for now. Like, you could FOIL that out, but don't. It'll cancel out nicely. And then the denominator, we're going to end up with an x plus 3. That's as your first. The middles, so that's when I'm just doing the square root times the square root. The outside and the inside cancel. And then we have the minus 2 and the plus 2 to give us a minus 4. You good so far, Destiny? Perfect. And then let's now do one more step of algebra, just bringing down the limit. X minus 1, still have the square root of x plus 3 plus 2. And the denominator, we could go ahead and simplify to that x minus 1, the plus 3 minus 4, which at this point we cancel the minus 1s. And we now plug in to have 1 plus the 3 in the square root plus 2. Technically all over 1, don't need to write it, but just felt like staying on top of it. Okay, that was terrible. So this is the square root of 4 plus 2, which is 2 plus 2, which is 4. That problem was not a bore. Maybe a little bit of a chore. I'm done. Before I make you snore. What? Any questions on this one? Awesome. So that's another approach that you'll run into, primarily involving square roots. So, everyone good on that one? Looks like it. So this next one is really tasty. Sometimes it's called the sandwich theorem or the squeeze theorem. See, sandwich joke. I just figured I'd let that one go. Okay. All right. So I was very punny today. So it sounds really funny, but it really is describing what's going on. So let's look at this picture and let's just make sense of it. And then a theorem, by the way, a theorem is just a property that's been proven to be true. So it's something that it's a method you could rely on in any case under certain conditions. So we have three functions here. We have h and g, and as a function that's on top and bottom, and then we have f right here in the middle. And what we're trying to find is, if you look at this point C, what we're trying to do is find let me do it in blue to match the color of f. So the limit as x approaches c of f of x, we're trying to figure out what is that equal to. And suppose we really don't know what f of x is. If you look at this, I hope f is okay. He seems to be up and down, he's just all over the place. But if you look at f, it is contained nicely between these two functions right here. Everyone agree? And again, it doesn't necessarily have to be on its whole domain. It could just be on a little piece. So it could just be on this piece. It doesn't have to be the whole domain, but it's a piece of the domain has got that erratic function in the middle contained. The reason this is called the sandwich theorem is because if you know what f and g, if you know what those are, h and g, and you can find their limit and they are equal, then you also could find the one right here. So I'll say this in words. If we know that the limit of x approaches c of h of x is equal to the limit as x approaches c of g of x, and they sandwich, quote unquote, sandwich or squeeze f of x, then the limit, or then I'll just say it this way, then we know the limit as x approaches c of f of x, because it is squeezed between them. Good thing I went to lunch before this, or I'd be really hungry right now. Good thing I handled this on a Friday, not a Tuesday or Thursday. So that's the squeeze theorem. Let's go ahead and make it a little more concrete using these examples down here below. This is the statement of what I just said in maybe more rigorous terms. Notice here, this inequality is the sandwich part. And this is saying if we can find the limit of f of x and g of x as x approaches c, and we know they're equal, that limit is the same for f of x. So you can see right here, we have a sandwich set up right here. We have two tasty parabolic functions, and it is sandwiching this blue piece of meat, which probably shouldn't eat it if it's blue, but just health recommendation. So you can see in that black box I drew that you have an upper and a lower function, and they are sandwiching, are squeezing this middle function, which we don't know, so we'll just call it u of x. So what this sandwich theorem is saying is, let's check the limit of the top function, so the red one. So let's go ahead and check the limit as x approaches 0 of 1 minus x squared over 2. Try plugging it in. It's 1 minus 0 over 2, which is 1. Let's try the bottom function, which I'll do orange, just because I don't think yellow would show up very well. This is the bottom function. The limit as x approaches 0 of, let's see, this is, oh, I messed up the top function. That should have been a plus. It didn't make a difference, but might as well keep my functions correct. So there was a little typo right there in blue, just to fix that. The bottom function is going to be 1 minus x squared over 4, which is 1 minus 0 over 4, which is 1. Are those two limits the same? Yes. So what we can say, because, wow, there we go. So notice that these are equal because the above limits are equal. What we also know is that the limit as x approaches 0 of u of x, even though I have no equation to work with, is 1. So that's the idea of the sandwich theorem. We won't use this one as much because honestly, kind of at this point in your mathematical learnings and development, it's a little hard to figure out those functions. But if I am assessing the sandwich theorem, I'll kind of provide functions that satisfy that. So kind of just think about this conceptually, like if you have a sequence of 3 functions in this inequality, check the limits of the outer functions, and if they're equal, then you know the limit of the inner function. It's sandwiched them. All right, so the most common scenarios at this point to find the limit will be let me ask you, what should you always try first? Plug it in, and if plugging in doesn't work, what should you then try to do? Factor and cancel. And then if you get some special cases, like if you get the square root, by all means, try that. There's a couple other additional examples right here I just want to talk about. You'll encounter these in your homework. So So I'm not going to do the full problem. I'm happy to do the full problem on a flex day, but I just want to expose you to some things that you'll encounter in your homework. So again, first thing you'll do here is 2 to the fourth minus 16 over x minus 2. Try putting it in. 2 minus 2. So this is 0 over 0. So you may try to factor and cancel, and you get, what do we have here? We have x to the fourth and 16. So remember, that's still a difference of squares where you have x squared plus 16, and then you have x squared minus 16 divided by x minus 2. So you're still going to run into 0 over 0, but notice right here, you have another difference of squares. I did make one mistake right here, though. I think I got a little too focused on the difference of squares. What was my mistake? It should be 4s, not 16s. So let me correct that. This should have been a 4, and this should have been still a 4. And then this is still a different squares. Remember, there is no sum of squares. Sum of squares is you're just stuck with that. It's really quite something. Okay. Math jokes are terrible. Okay. So I'll leave the rest of this one for you to try out, but there's a little hint. Okay, number 19. Boy, this one is really just all cut up, isn't it? Fractions everywhere. This is sometimes referred to as a compound fraction. To figure out compound fractions, there's various approaches you could do. My suggestion is always just try to get common denominators in each part. So if you look at this, we have the numerator, and then in the numerator, we have two fractions. So what you can go ahead and do